All right, guys, in the last few videos, one of the topics that we covered was the concept of a Thevenin equivalent circuit. However, we really didn't get very much practice in working with these circuits. One word of warning that I really want to give you guys before we head in and start going through an example is that by this point in the class, we've developed multiple techniques of circuit analysis. Now, most of the circuits and most of the times, you've been given the circuit, not just the circuit to analyze, but also been told what technique to use. At this point, however, you can use to analyze oftentimes the two circuits that we'll be working with to find the Thevenin or Norton equivalent circuit. You can use any technique of circuit analysis at your disposal. At this point, it is your choice as to which technique to use. Right. So the example that I have in mind is the following. We have a circuit here that contains an independent voltage source providing us with 72 volts. It's hooked up to a network of resistors that look like this. There's a terminal A up here, a terminal B down there, and there's one last resistor on the very top portion of the circuit that looks like that. These are such that this is a 20 ohm resistor, an 8 ohm resistor, a 5 ohm resistor, and then lastly, a 12 ohm resistor. Now, the goal of this problem is to find the Thevenin equivalent circuit to the one above, and this is with respect to the terminals A and B. So here what we're doing is we're looking in through these two terminals and finding the Thevenin equivalent circuit with respect to that. Keep in mind that the Thevenin equivalent will change depending on the terminals that you look into. However, here the Thevenin equivalent circuit to the one above is going to be composed of a voltage source that happens to be in series with a resistor. This is the Thevenin voltage, this is the Thevenin resistance, and it is these two things that we're actually going to be looking for that are going to be our solutions to our problem, right? So we're looking for the Thevenin voltage and the Thevenin resistance. Right? And the way we're going to find these things is by considering two separate circuits. From theory, one of the things that we covered was if we're actually given the circuit here up top, if we consider the open circuit and find the open circuit voltage, then that's actually going to be our Thevenin voltage. So for part one of this, we're going to consider the open circuit. This will allow us to find the open circuit voltage, and from theory, this is the Thevenin voltage. So we'll have one of the two pieces of the puzzle that we're looking for. We'll actually use the circuit to find this. So let's draw that open circuit. So I'm going to recopy this entire circuit. So here I have my 72 volt source. I have the same network of resistors in the same spot. So here they all are. I still have my terminal A and my terminal B, like so, and these have the same value. So this is 22 ohms, or I'm sorry, 12 ohms. I can't all of a sudden just change the value of these. That wouldn't be good. So this is 12 ohms, this is 8 ohms, this is 20 ohms, and lastly, this is 5 ohms. Now, the open circuit voltage is this voltage with this particular polarity across terminals A and B. And again, we can use any technique of circuit analysis that we want in order to do that. Now, I'm going to go ahead and use the node voltage method here. So I'm going to use the node voltage method. And the reason to use the node voltage method is simple, is I'm looking for a voltage. So if I use the node voltage method, once I solve my system of equations, that will give me that open circuit voltage directly. So I'm going to first identify all the nodes here. There's one big node here at the bottom. I already know that I'm going to choose this node as my ground node. Then I have to take a look at the voltage sources in order to figure out which node voltages are independent and which ones are not. Notice that there's a voltage source right here. So if I circle this node right there, then this node voltage is not unknown. It has a value of plus 72 volts. And it's because in going from the ground node up this way, I go through a voltage rise of 72. So that node voltage is not unknown, it is not independent, it's 72 volts. We then have a node voltage here. I'll call this node A and this node voltage VA. And notice that there's one last node here. And I have already said that the node voltage there is VOC, so I don't need a second name for that. I can just call this node voltage plus VOC. Right. So I'm now going to start setting up systems of equations in order to find what that node voltage happens to be. Right. Now, I am going to give this node a name as well, right there. I'll give that node a name, node B, and you'll see why I do that here in a second as well. So I'm going to use KCL at node B, and the convention that I'm using is that the sum of the currents flowing out of this node have to add up to 0. Actually, let me start with node A. So I'm concentrating on this node there. Notice that there are 3 separate components hooked up there. So here in the sum of my currents, I have 3 separate terms that I'm going to write. So at node A, concentrating on that branch, the current flowing out of there is VA minus the 72 volts over here, and divided by the 5 ohm resistor that current is flowing through. Then I have, for this branch, the current flowing out of there is VA minus the ground node, that's 0 volts, divided by the 20 ohm resistor that current is flowing through. And then lastly, whoops, I deleted the whole thing. Let me put that back where it was. Lastly, we have the current going through that branch, and that is plus VA minus VOC over the 8 ohms. Those must add up to 0. Now, one thing that we can do to clean this equation up just at least slightly is multiply everything through here by a common denominator, and then I'll group terms very nicely. So the common denominator here should be 40. So if I multiply everything through by 40, 40 divided by 5, well, that's 8, and I can actually multiply that through. So this is 8 VA, and then 8 times 72, I can't do that in my head. Luckily, I've got my calculator here, so I've got 72 times 8. That is minus 576. I then am going to multiply through by that, and that's going to cancel out to 2, so I have plus 2 VA, and then I'm going to distribute to these terms here. The 40 divided by 8, that's 5, and I can distribute to both of those, so I have plus 5 VA minus 5 VOC. And then lastly, and this might be kind of trivial, but this 40 does multiply the 0, and that gives me 0. I can group my like terms. Notice that I have quite a number of VAs there. 8 plus 2 plus 5 gives me a total of 15 VAs. And then I have minus 5 VOC, and that's equal to 576. Right? And this is an important equation. I'm going to go ahead and label that as equation 1. Now, I need 2 equations in order to form a system of equations. The other node where I can actually use the node voltage method to construct another equation is at this node. This is node B. So here, let's go ahead and do that. So I'm going to use KCL at node B now. So the sum of the currents flowing out of this node must add up to 0. Now notice that at this node there are a total of 2 components. So when I set up my system, it's going to be a sum of 2 components. So here, at this particular node, let's write down the node voltage equation for this branch, and that is VOC minus the 72 volts on the opposite side that is flowing through the 12 ohm resistor. And then I have going through that branch, and the current there is plus VOC minus VA. That is flowing through the 8 ohm resistor. That must add up to 0. Once again, I can clean up this equation by multiplying through by the common denominator. Here the common denominator looks to be 24. So I can multiply everything through by 24 and then distribute. So 24 divided by 12, that's 2, and I can distribute that to VOC. So I have 2 VOC. 2 times 72 should be 144, but let's confirm that. Yeah, so 144 minus 144, and then I can distribute this to that. 24 divided by 8, that's 3. So I have plus 3 VOC minus 3 VA. And then lastly, I can distribute to the 0, in which case I get 0 here. I can clean this equation up as well. I have a total of minus 3 VAs, 5 VOCs, so this is minus 3 VA plus 5 VOC. And this minus 144, I can actually add to the opposite side at the expense of that minus sign to clean it up a little bit. This is the second equation that I wanted, and I'll call that equation 2. So now we have a very clear system of equations. So we have our system of equations here. The first equation was 15 VA minus 5 VOC is equal to 576. And then my second is minus 3 VA plus 5 VOC is equal to 144. Now you can use any technique of algebra that you want in order to solve these. I'm going to go ahead and use my calculator to solve this system of equations. So using my calculator, we're actually going to get a value for VA. We're going to get a value for VOC. So here I have a system of equation calculator. this is a system of two equations with two unknowns. So the first one is 15 VA minus 5 VOC is equal to 576. And the other one is negative 3 VA plus 5 VOC is equal to 144. And when I solve this, I get VA is 60 volts and VOC is 64.8 volts. Now, this was the very thing that I was actually after. This value of the open circuit voltage is equal to the Thevenin voltage. So we now have the first piece of our puzzle here, like this. So going all the way back up here to finding this Thevenin equivalent voltage, right, we now know that this is 64.8 volts, right? Now we're going to consider the second circuit. So this is going to be for part 2. We're actually going to consider the short circuit. And this is going to allow us to find the short circuit current. And we then know that our Thevenin resistance is the open circuit voltage that we found before divided by the short circuit current. This will allow us to find the second piece of the puzzle. We'll be good to go with that. So I'm going to go ahead and stop it here and then take a look at the next problem. So here's my original circuit. I'm going to redraw it. And then what I'm going to do is between these two terminals, A and B, I am literally just going to short circuit it. I'm going to place a wire there. There is going to be a current that flows from terminal A down to terminal B. That by definition is your short circuit current. And we can use any technique of circuit analysis that we want in order to find that. So let me go ahead and draw in the circuit that we're going to be working with. It still consists of our 72 volt source. We still have these resistors in the same place, like this. And this has a value of 12 ohms, 8 ohms, 5 ohms, and then lastly 20 ohms. And then where we had terminal A and B, like this, what I'm going to do is I'm going to short circuit this, and there is going to be a short circuit current that flows this way. Let me clean this up a little bit more nicely. So here, this is the same thing. Here's terminal A, here's terminal B, and there is a current going down this way, short circuit current, that we want to find. And again, we can use any technique of circuit analysis that you want in order to find that. Just to switch things up to show you that you can use any technique whatsoever, I'm going to use the mesh current method to find this. Why? Because if I set up a system of mesh currents, right, when I solve that system, the short circuit current is going to be one of them, right, where I can use those very easily to get that short circuit current. So here, in my meshes, I'm going to say that this is mesh number 1. There's a short circuit current flow, or a current flowing in that mesh. This I'm going to call mesh number 2. And then lastly, I'll call this mesh number 3. Right? Like this. So I'm going to use the mesh current method. To set up a system. And then I'm going to use my calculator to solve. Like this. So if I use KVL, around mesh number 1, remember it's the sum of the voltages around this mesh that must add up to 0. So I'm going to start here, and then I'm going to go in this direction, like this, through each one of those components. So I'm kind of following the same direction in my loop, right? So as I go from that node up through the 72 volt source, notice that I am going through I hit the minus sign first, so into KVL goes minus 72 volts. I then go through my 5 ohm resistor, and I'm going in my direction, my loop, I'm going in the same direction as I1, and I'm going in the opposite direction as I2. So I have the term I1 minus I2. That is the voltage that you get as you go through that resistor. Then I go through this resistor, and as I go downward through the 20 ohm resistor, I am going in the same direction as I1. I am going in the opposite direction as I3, so it is I1 minus I3. Those are the only components in that loop. The sum of those voltages must add up to 0. Notice that, once again, I can distribute some of these and group-like terms to kind of clean up this equation. So this was 5 times I1. So 5 times 20, 5 plus 20, that is 20 I1. I have minus 5 I2s. I also have plus 20 I3s. And I can add that 72 to the opposite side, like so. I'll call that equation 1. I then am going to use KVL around mesh number 2. So the sum of the voltages around this new mesh must add up to 0. So once again, I'm going to start here, and I'm going to go in the same direction, like that. I first go through the 12 ohm resistor, so that is 12, and I'm going in the same direction as I2, so 12 times I2. I then go through the 8 ohm resistor. You have I2 and I3 there. So this is 8 times I2 minus I3. I then go through the 5 ohm resistor, and I2 and I1 exist there, so it is I2 minus I1. Those must add up to 0. I can clean this equation up as well. So I have minus 5 I1s from the last term. I have 8 I2s from the second term, from here, and then 5 I2s from that one. Similarly, 12 from that. So 12 plus 8, that's 20, plus 5 more, that is plus 25 I2s. And then lastly, minus 8 I3s. Those must add up to 0. This is going to be my second equation. Lastly, I have one last mesh to exploit. So I'm going to use KVL around mesh number 3. So the sum of all of those voltages around that mesh must add up to 0. So I'm going to start here, and I'm going to go in this direction. Notice that there's only 2 components that I'm going through. So here, when I go through the 20 ohm resistor, the voltage that I pick up is 20 ohms times I3 minus I1. When I go through the 8 ohm resistor, this is plus 8 I3 minus I2. These must add up to 0. And let's distribute and clean this up. So I have minus 20 I1s from the first term. I have minus 8 I2s from the second. And then from the third, I have 20 from there, 8 from there. I can group those together to give me plus 28 I3, and that's equal to 0. This is going to be my last equation needed. I'll call that equation 3. So I'm going to use a calculator. To solve this as a system of equations. And the system of equations that I'm plugging into my calculator are equations 1, 2, and 3, and I've put them into standard form so that it simplifies putting it into the calculator. But I will get a value for I1, a value for I2, a value for I3, and then we'll go back to see how that compares to the mesh currents. So here, I'm going to solve using my system of equations calculator. So I have 20 I1 minus 5 I2 plus 20 I3, that's equal to 72. I then have minus I1, or minus 5 I1 plus 25 I2 minus 8 I3, and that's equal to 0. And then the last equation is minus 20 I1 minus 8 I2 plus 28 I3, and that's equal to 0. And if you happen to solve this, I ended up with a very strange result. Did I plug them into my calculator wrong? Let me double check. Double checking your calculator calculations if you find something that's a little bit strange is always a good idea. As professors, even we end up getting these things wrong from time to time. Let's see, where did I make my mistake? I know I plugged into my calculator incorrectly. It's a matter of finding where that happens to be. Oh, no, here it is. This term right here, I1, this should be 25. So I've got 20 from there, 5 from there. That adds up to 25. So again, even as instructors, we have to double check our work. So here, if we go back, let me go ahead and copy this and change it. This. Okay, it's not wanting to do it, so let me just go ahead and solve it again. So in my system of equations, we have not 20 I1, but 25 I1. Minus 5 I2 plus 20 I3, that's equal to 72. Followed by minus 5 I1 plus 25 I2 minus 8 I3, and that's equal to 0. And then minus 20 I1 minus 8 I2 plus 28 I3, and that's equal to 0. Let's turn these into numbers. And once again, I'm getting something strange. So I think I might have to edit this. So let me see.
If you have the numbers from your PowerPoint.
Yeah, I'll just go ahead and use that. Okay. So using a calculator, I found that I1 is 12.72 amps. I2 is 6 amps, and lastly, I3 is 10.8 amps. Exactly. Let's clean that up. Right. Now going back to the circuit, I3 lives along the perimeter of this mesh. Notice that it matches up with the value of the short circuit current that we're looking for, not just in terms of magnitude, but also direction. Therefore, immediately from these results, we can actually see that I3 and the short circuit current are the same thing. This is what we were looking for. This is the portion that we want to box like this. This also means that we can go back up to our previous results. We were trying to find the Thevenin resistance. We now have all the pieces that we need. So the Thevenin resistance here is the open circuit voltage divided by the short circuit current. We found the open circuit voltage to be 64.8 volts. Our short circuit current we just found to be 10.8 amps. That means that we can calculate this. Thevenin resistance to be 64.8 divided by 10.08. And this gives us a very pleasing result of 6 ohms. This was the last piece of our puzzle here. That means that all the way up here, the Thevenin resistance that we were looking for is this. This is 6 ohms. So let's actually just clean this up very, very quickly. Our Thevenin equivalent circuit to the original consists of a voltage source, where the Thevenin voltage is the 64.8 volts. The Thevenin resistance is the very pleasing 6 ohms. And then we have our terminals A and B. So this is our solution. Hooray! Sounds perfect. So anytime we see this larger circuit up here, we can always replace it with its Thevenin equivalent. Thank you for watching.